So today we've been just doing calculation after calculation. But today I want to talk about some theoretical considerations regarding the Laplace equation and also the heat equation and so on. So the first thing I want to say is recall that divergence is the density of flux, and that's actually what we call the Green's theorem. So when you have some domain D, and you have some vector field that's crossing it, then you're interested in whether more vectors are trying to escape this region or more vectors are trying to go into this region. And the flux is defined as the integral around this boundary of D, where you take the vector field F and you do a dot product with the outward normal vector N, so that this only picks up the component of the vector that's trying to escape the region, and then you integrate around this thing. Okay? So that's what's called the flux. Right? And this statement that divergence is the density of flux, it means the following. It means that if you take the divergence of F, and if you multiply by the area element, then over a small domain, so let's say this is your dA, very small domain, density times area. By the way, this density is the area density, so that if you multiply the density by the area, you recover its physical quantity. So the flux over this small region is computed by doing this. And if you add up fluxes over these small regions and add them up everywhere, that's like integrating over the entire D, that's going to give you the flux around the entire domain D. So there's this identity between the two, and that's called the Green's theorem, the divergence form of the Green's theorem. Okay? It's the one that's used less often than the other form, the curl form of the Green's theorem, but this is the one that we have to use today. Okay? Now let me say a little bit more about the divergence of F. So in the case when the vector field is a gradient vector field, and we're talking about the two-dimensional case here, so gradient would be take the partial with respect to x and partial with respect to y. The divergence of F is defined as, this is what we call nabla dot of F. And this nabla it's a vector form of an operator. So it's a differentiation in x and differentiation in y. That's what we call the nabla. Okay. So if you look, this one here, I don't want to write it here, but let me write it here. So when I say nabla u, what does that mean? That means you apply this round x, round y to u. So when you do scalar multiplication so that this gets multiplied both sides, so you get round x, round u, round xu, and then round yu. Okay. So that's why this is ux, uy. Okay. So that's what gradient is. Okay? And if you apply the nabla and do a dot product with f, which is already of this form, this would be, how do you do dot product? The component-wise multiplication and you add, right? So you're taking you're taking ux, which is already differentiated once in x, do another derivative with respect to x, right? So that's going to be uxx. And then if ui means it's already differentiated once in y, so if you differentiate twice, that's uyy. Which we call the Laplacian of u. So what I just demonstrated is that, in other words, divergence of the gradient of u is the same thing as the Laplacian of u. That's what the above calculation is saying. But that's not what I'm aiming at. I'm trying to rewrite this in the form of u. Okay, so let's try to write this in the form of u. So we have gradient of u. So ux, uy as a vector dotted with n ds is equal to, oh, we should get single integral, and then double integral over d of u dA. So this is what we get. So true for any differentiable, actually twice differentiable, not right, differentiable u. Okay. So if u can be differentiated twice, then that would be always true. Now, what can I prove using that? Well, so the main theorem that I want to present is the mean value property. So theorem. Mean value property of harmonic functions. Mean value theorem, mean value property of harmonic functions. And the statement is the following. What's a harmonic function again? Yeah, when the Laplacian is equal to 0. Okay? So if Laplacian of u equal to 0, and D is a disk of radius r, with center at a comma b, then the following holds. U of a comma b equals to 1 over 2 pi r of integral of over the boundary of D of this U ds. And also, u of AB is equal to 1 over pi r squared of a double integral over d of u dA. That's the mean value property. And because a disk of radius r has the boundary as a circle of radius r, what's the circumference of circle of radius r? It's 2 pi r, right? Mm-hmm. So what is this doing? You're adding up all the values of u around the circle and you're dividing by its circumference. So that's like taking the average. That's the mean value, right? That's why this is called the mean value, right? So before we actually prove this, let's think about what this means. It means that if u is harmonic, then at any point you can draw any circle of radius r, right? And the average value of this around the circle, right, is same as this point. Average value around here is same as that. Okay, that's what this first statement is saying. And it's also true that if you take the average of the entire value of u, so you're adding up all the values of u and you're dividing by the size of this disk, right? That's again average, right? How do you calculate averages again? You add everything and divide by the number of data points, right? Yeah. But if you think of that in terms of calculus, you just integrate everything and you divide it by the area of that region or length of that region. That's how you calculate area, right? So the average value of u over this entire domain should also equal to this, okay, on a circular region. So that's what's true. Okay. So let's try to prove this. Proof. So what I want to do is to think about this parametrization. So the circle centered at A comma B with radius r, if you parameterize this by using theta, it's like this. X would be A plus r cosine theta, and y would be A plus r sine theta. Right? So, I mean, without the, not A, sorry, it should be B. Without A and B, if you just have r cosine theta and r sine theta, that's just the polar coordinate system, right? All you're doing is you're just shifting the polar coordinate system so that it's centered at A and B, right? Okay? And then what you want to do is you integrate u A plus r cosine theta, comma B plus r sine theta, d theta, where theta goes from 0 to 2 pi. So that's going to be your boundary of d, u, ds. So we're not going to think about 1 over 2 pi r for now. We're just going to do this. Okay. Okay, so let's try to think of this now as a function of r. Okay? Oh, there's something that I should have thought about just a minute. There may be some factor here. If you right. Oh, this is not that clear at all. Sorry. If I say R is this thing. So usually you put this as like some vector. So this is a R in bold. It's different from this R. Okay, RT. What is R prime of t? That's going to be, if you differentiate this by theta, then that's going to give you R negative R sine theta and R cosine theta, right? And what is this? That's dr over dt. Okay. So let me do this over.
Do you mean d
Theta.
theta?
Let's put this as t. I'm used to this t in the multivariable calculus. So let's just use t. Although it's really theta that I'm thinking about. Okay. This is t. So you have dr dt as this thing. Okay? So how do you actually calculate this? Well, so a priori, we don't know how to do this. I would write this, but then if somebody told me to calculate this, at first I would have no idea because I don't know what ds is. Right? So what you do is you want to make meaning out of this, and you do it by dividing by dt and multiplying by dt. Right. Now, what is the nature of S? S is the arc length. Right? So when I say I'm adding up u by ds, that means I have values of u over here, and then I have this ds, very small arc length. So I multiply ds by the value of u, and you add them up around this entire thing. That's what this means, right? Okay? And this one is, what is dr? Well, dr is also like arc length. The difference is that this is a vector. Okay? So it has the magnitude, same thing as the arc length, but it has also the direction, the tangential direction to this arc. Okay? So what will be the relationship between ds and dr? One is the norm of the other. Okay? If you just forget the direction, you get this. All right? So the way you calculate this is by doing, you take the norm of dr dt, but then what's the norm of this? The norm of that thing will be square root of negative r sine t squared plus r cosine t squared. All I'm doing is the norm of a vector. You know how to do a norm of a vector, right? Square, square, take the square root. Right? That's what I do. dt. And then what do you get here? What do you get? Huh?
Give me 1 second.
R squared, then you get sine squared, then cosine squared. What's sine squared plus cosine squared? 1. So what do you get if you simplify this? R squared, and you take the square root, you get R, right? Yeah. So what happens is that if I have 1 over 2 pi r here, you end up with just this. You end up with equal to 1 over 2 pi of integral from 0 to 2 pi, because the t is like the theta, it's the angle you go around the circle, is 2 pi, of this u evaluated at r, which is a plus r cosine theta, comma b plus r sine theta. And then r was already canceled out, and you only have t left. Is that good? So this is a nice lesson in multivariable calculus if you forgot how to do line integrals. See, line integrals come in 2 flavors. Did you notice that when you do in multivariable calculus? There's this line integral over some c, and there's this line integral over some c. What's the difference? Well, here f is a scalar valued function, so you multiply by a line element, and you just multiply and you add. And the value of this is like you have some curve and you have some function over it, and it's like the curved area over this thing. Okay? Whereas this is different. Here the vector f is a vector field, and dr is a vector quantity, so you can do a dot product. So you do the dot product, and this has the meaning of if you have some vector fields going over this arc, then it's like the work done by this vector field, because it looks at how this point is going over this path, and you're just adding up all the vector fields. You're doing f times the distance, which is the work. So you're adding this, and that's how you get the work done by the vector field. And in both cases, if you want to actually do the calculation, always the idea is to divide by dt and multiply by dt. That's how you do the work. Okay. So it's something nice to remember. All right. So let's see. Let's denote this as some function of r. So we'll call this phi of r. There's Greek letters to just freak some people out. Now, what happens if I do a derivative of phi of r? Let's see what happens then. Well, then derivative just goes into here, because the only place you have r is here and there, right? There's no other dependence in r. So this is going to be 1 over 2 pi of 0 to pi. And then we're going to think of this as like, this one is your x, that's your y, right? So, see, we actually have to do derivative of u with respect to dr, dt. That's what we have to do. But u has the following dependence diagram. U is a function of x and y, and they're both functions of r. Right? So what does the chain rule say? The chain rule says you first have to do partial of u with respect to x, and then you have to do dx dt plus uy dy dt and dt. Oh, sorry, dr. Okay? That's what the chain rule says, right? So if you wanted to know how u changes with respect to r, there are 2 ways that change of r affects u. one going through this way and another going through that way. This way is you see how u changes with respect to x, that's ux. Multiply that by how x changes with respect to r, that's dx dr. You multiply these two, that gives you this quantity. Same thing, that gives you that quantity. Adding the two gives you the total change, rate of change of u when you change of r. Okay? Now, tell me what dx dr is. What's dx dr? You're taking this and differentiating by r. What do you get? Cosine theta. Cosine t, sorry. Should be t. Decided to call it t. Okay? So you have the following. You have ux times cosine t plus uy, and then what? Sine t. Okay, and then you can further rewrite this as a ux comma uy dot with cosine t sine t dt. Now it starts to look like something that I just said, right? So look at this picture. We have such a circle, right? At each t, t is the angle from. Maybe I should just say it again. So t is the angle from the positive x-axis, right? And then at this point, what's this vector? Cosine t comma sine t, right? This vector is cosine t comma sine t, so this vector should also be cosine t sine t. So in other words, the outward normal vector at t is exactly cosine t comma sine t. Is that good? Yeah. So this is going to be equal to 1 over 2 pi, 0 to 2 pi of ux uy dotted with dt. Now, one thing that you might not like is that here we have ds and there's dt. Well, we can always go back. We know that the relationship was that ds is equal to r dt, right? Okay. So we can actually go back and say, oh, this can be replaced as 1 over 2 pi r around the disk of ux uy of ds. So we can go back. Okay. So rewrite dt is equal to ds over r, so you can bring the r outside. So these two are still the same. Okay. So now we're almost done. What does this equal according to this theorem here? It's the 1 over 2 pi r of double integral of Laplacian of u dA. Now guess what Laplacian of u is? I think you're still processing the previous calculation. Do you want me to explain any of the previous calculation here? I think I actually did my best. I think I explained everything, every little detail. This is the usual chain rule, multivariable chain rule. Okay, so what is Laplacian of u? 0, right? That's given here. 0, right? So that's going to be 0. Okay. Using this, we prove that this is 0. Okay. So what does that mean? If this is true, that means phi of r is constant. Now, remember, the meaning of phi of r is the average value over a circle, right? Now, that's constant. Think about shrinking your r smaller and smaller down to 0. What happens? There'll be a very small circle around this a comma b, right? Yes?
Can you remind us, how do we conclude that that is phi of r?
So our condition is that Laplacian is 0.
Yes.
Okay? We had to make use of this one, so we worked really hard to make this at 0. And because this calculation it began with the derivative of phi of r, right? So our current conclusion is that the derivative of this function is 0. What functions give you 0 if the derivative is 0?
It's a constant.
It's a constant. That's what we're saying.
Okay.
Okay?
Thank you.
And now I'm trying to explain what that means. If it's a constant, then think about this extreme case when r is set to 0. In a small circle around a comma b, the value of that average will be close to what? The value of a comma b, right?
Yes.
Yeah. So so here's the punchline. Since limit of r going to 0 of phi of r must be equal to uab, right? We see that phi of r must be equal to that value. So for any radius r, we have shown that this value is given as that one. Okay? Is that good? Yeah. Now for this second one, I'll just have to hand wave because this is already too hard, and I think you won't be able to really follow this one. But it's almost free after this because if you integrate over a disk, you can think of this as integration over each of the rings, right? So you can integrate everything as these rings, and then you're taking the average. But the average value over each ring is same as this value at the center, right? Therefore, if you take the average over a whole disk, it will still be the same as the value at UAB. That's what it means. And I can use, how you use polar coordinates like r d theta. You remember this? Find dA equal to that. So I can use that and make this integral over the disk as integral over each of the circle, and then change the radius r, and then do some more calculations to show that for each of the rings that you integrate, it's going to always give you the value of this. Therefore, if you calculate on the whole thing, you get that. So that's like the basic idea. All right? Okay, so that's the mean value property. Now, mean value property has some really nice implications because, so let's have some discussion about what this means. So what does this mean? Well, first, let's kind of have an intuition why this is true. Like, even if you didn't see the proof and if you didn't follow everything 100%, why would you actually believe this if somebody told you? Well, you remember how we said these harmonic functions, they look like saddle points, right? So look at a saddle from above, right? So if you have a saddle such that It's like, so you go up this way, up that way, but then there's this way you're going down, right? Now, if this is the case, if you integrate around the circle, don't you see that over here you're going over this value, you're going over that value, but over here it's going under that value. So somehow they cancel out, so that if you average out, it's the same as the value in the middle, right? Yeah. So that's why. Like, yes.
Is it because the symmetry and if you slice it with this? Like
No, this is all I can say. I mean, if this is 0, that means it looks like, locally it looks like a saddle point. If it looks like a saddle point, that means like, if it's not a constant, if it's constant, then of course this is always true. And if it's like a plane, that's also true as well. But if it's curved, then what it means is like it looks like a saddle, and over a saddle some points go up, and it's like a Pringles. So yeah. Yeah. So next time you hold a Pringles chip, you should be thinking of harmonic functions. Keep being weirder. As if you want to become a mathematician, like you need to have these strange linkage between everyday things and math. All right. So this is what it means. This is what it means. Okay. So I guess number 1. It's a saddle point like, or saddle like geometry. So the shape is like saddle. Number 2, very smooth. Because if you average out something, then averaging process makes something smoother. Right? So, I mean, I don't know if you ever. So if you had some picture, you can do Gaussian blur and stuff like that. Have you done like photo editing? Have you ever tried like Photoshop and do Gaussian blur? What does blur do? You take neighboring points and you take the average value and place it right here. That's what blurs do, right?
Oh.
That would be what it is, right? That's what blurs would do. And if that's what's happening, think about the result of the blur. If you had the original picture as very sharp, right? After blur, what happens? It becomes like a gradient, right? It becomes gradual. So it becomes smoother. The changes become smoother. Do you agree? Right? So as a result, you can show that if anything is harmonic, then it's infinitely differentiable. It's very, very smooth. Okay? So that's the outcome of this mean value theorem. Now a third one is another theorem that's very important, but I'm just going to hand wave from here. It's called the maximal value property. Or maximum value principle or something like that. Yeah. What it means is that the maximum can only appear at the boundaries. Okay. Or else it's a constant. And this one, already this Pringles-like geometry would tell you that. Like if you hold a Pringles chip the highest point is always at the boundary, right? Yeah. And the lowest point as well. So maximal value property also means the minimum value property as well. But the proof of this actually can be argued from here. So suppose you have some domain, some region here, and here this is 0. Okay. Now, I want to argue that if an interior point has a maximum value, then it must be a constant. Okay. How do you do that? Well, first, choose that maximum value, choose a circle, choose a disk around it. Okay? We know that the average of this disk is same as this. But since this is the maximum possible value of u, you can't have anything that's higher than this value here. So what must happen? It has to be constant. That's the only way. Right? Then if this is all the same value, then you can continue on, putting disks around everywhere. And you end up saying that every value here should be the same value as the maximum. So for this harmonic functions, you can always find the maximum and also minimum. If you prove this, since if u is harmonic, negative u is harmonic as well, because Laplacian of u and u is, if Laplacian of u is 0, then negative Laplacian of u is also 0, right? So the minimum value also is true as well. Okay, so the maximum and the minimum value of a harmonic function must happen at the boundary. Okay, so that's what we've proved. So this one thing actually says a lot of things, and then there's this fourth thing, which is not directly from here, but I'll just write as note. So note. The converse is also true. So if UAB is equal to 1 over 2 pi r of boundary of a disk of UDS for all disk, right? All disks, then Laplacian must be 0. Okay. So that's something else that you can prove. So in other words, this mean value property captures everything about the harmonic function. Okay. If it's harmonic, it must have this mean value property. If a function satisfies the mean value property for any circles inside the domain, then it must satisfy this. Okay? So that's just the secondary thing. And this actually gives the first uniqueness theorem that I promised. So I promised that I might show you some uniqueness theorems. So the context was that do we solve differential equations? No. What do? We make guesses, right? And if it works, it works. Why? Because we know the solution is unique. Okay. So having a uniqueness guarantees that the solution we found is everything, and we don't have to look for anything else. Okay. So let's think about the following thing. Okay. So corollary of maximal principle, or maximal value property, is the following. If uxy and vxy are both solutions of Laplacian of u equals to 0, u 0 comma x equals to f1, u L comma x, no sorry, this should be y, f1y, u L comma y is equal to f2 of y, u of x comma 0 is equal to f3 of x, and u x comma m is equal to f4 of x. Then u xy must be equal to v xy. Triple equal means that they're equal as functions. Okay? They're completely equal inside this domain. So the domain here is here's m, and then here's l. So if inside this rectangle Laplacian is 0, and if their boundary values are equal, then it must be that. Okay? So let's prove this. Proof. Well, set wxy as uxy minus vxy. Okay. Then guess what kind of equation w satisfies? So then, what's the Laplacian of w? Zero, right? Because Laplacian of u is 0, Laplacian of v is 0, right? We're assuming that v also satisfies the same exact property, okay? All right. And then what is w of 0y? Do you notice something? A lot of times when I ask something, the answer is 0. That happens in a lot of harder math courses. So, yeah, the answer is 0. Okay. Why? Because you're subtracting, and it's f1y minus f1y. Both of u0y and v0y are f1y, so f1y minus f1y will be 0. Agreed? Okay. And do you see that the other ones are the same as well? What's uly? 0. Right? What's u of x0? 0. What's u of xn? 0. Okay. So what's the max value of w is what? We know that the maximum can only happen at the boundary, right? Yeah. So what is the maximum value of this? On the boundary, it's all 0, right? What's the maximum value? 0. I told you the answer is 0, okay? Yeah. All right. So max value of w is 0, and minimum value of w is 0. Okay. So what's a function whose maximum value is 0 and minimum value is 0? Okay. And this is by Maxwell property, maximum value property. So from this, we see that w is always 0, even inside the domain. Okay? But that means u minus v is equal to 0 inside the domain, so that we see that they're the same. So done. Right? What does that tell you? That there's only one unique solution to such a problem. If you think you found something else that satisfies the same equation, well, this shows that something else has to be same as the original one you found. Okay? And that gives you confidence that whatever method you use, if it works, it works. Okay? So that's an example of a uniqueness theorem. Okay. I think if we have time, we can also talk about the uniqueness of the heat equation. All right, now we're going to move to a different topic. We're going to talk about Fourier series, but this is not yet the Fourier series, so I'm going to title this as Preparation for Fourier, not Fourier series, but Fourier Transform. We have to do some integral before we do the Fourier transform. How many of you have done Laplace transform in Calc 4? Did you learn Laplace transform? Okay, yeah. So depending on the professors, some have enough time to teach that. Some they don't have enough time at the end. They skip that part. But Laplace transform. Let me talk about the Laplace transform. Laplace transform of a function. Usually, the function is a function of t. And this is defined as, so I put a delta here, that means it's a definition. Integral from 0 to infinity of ft e to the negative st dt. And that usually this calculation is not so easy. So what you do is there's a table of Laplace transforms, and you look at that, and using that table, you can figure out what the answer is quickly. And engineers use this Laplace transform all the time because when they solve circuits or some mechanical vibrations problem, instead of having to solve the other ones, just looking up the table makes the process a lot quicker. So this is like the most favored method in solving differential equations for engineers. But the actual calculation is not that easy. So for example, on the Laplace table, you're going to see something like the Laplace transform of sine a t is equal to a over a squared plus s squared. Yeah. That's in the Laplace table. And then, but trying to actually get this is hard. So let me just give you an idea just by doing one simple case. Well, so just say a is 1, so that this is like 1. This is 1. So let's try to verify that this is actually true. Proof or calculation. So you're trying to do integral from 0 to infinity of sine t times e to the negative st dt. And this is a nice example I want to show you because in all the other tabular integration I showed you, it always hits 0 at some point. This one is something that it doesn't hit 0. And therefore, it relies on you to remembering at what point you have to stop. Okay. So, at least for the integration of parts questions that you need to solve on the exam so far are always the ones that hit 0. So you don't have to worry about this one. So I just want to give you a demonstration. Okay. So according to Lee 8. Logarithms, inverse trigs, algebraic, trigonometric, exponential. Exponential is on the far right, so e should be the one that's integrated. And trig is right before, so this has to be the one that's differentiated. And we have plus minus here. Now, if you differentiate sine t, you get cosine t. Differentiating gives you a negative sine t. And then at this point, you are kind of lost because it never hits 0, right? So the question is, when do you stop? And for this, you stop when you get the same kind of function as you started from the beginning. Okay, so ignore the constants. Other than the constants is sine t, right? If that happens, you stop. Okay. And so we stop here, and then you integrate this, and we integrate this. That's negative 1 over s e to the negative st. Integrate this. It's positive 1 over s squared e to the negative st. And then this goes plus, minus, plus. Okay. And then do this, right? So in both cases, it's negative 1 over s sine t e to the negative st from this first one, and then minus 1 over s squared cosine t e to the negative st. And there's this additional step that I did not bother to do because for us it was always 0 at the end. But there is this additional step you have to do because this is not 0. What you need to do is you have to multiply the last row, just like go straight. It's no longer this parabola, so you go straight, you multiply this, which is negative sine t e to the 1 over s squared e to the negative st, and you have to integrate that. And the sum of this plus this plus this is the original integral of this. Okay. All right, so let's see what we've achieved. And for students who did well in Calculus 2, you probably remember this one. So what is that? That's going to be, so here we start out by saying I want the integral of sine t times e to the negative st dt. And the result of the integral is negative 1 over s squared. Let's do this. Negative 1 over s squared, and then s sine t, and then plus cosine t, and then e to the negative st. So what I did was I combined these two. I factored out negative 1 over s squared out, and then e to the negative st. Since this 1 over s is s over s squared, that's why there's an s in front of sine t. Following? But then there's this last one, which is minus. Notice that 1 over s squared is independent of t, so I can bring it outside. It's a constant with respect to t. So I have 1 over s squared integral sine t e to the negative st dt. Right? And then you look at this, and initially this looks very foolish because you started with this question, and the answer contains the question that you started with, right? Yeah. That's like circular reasoning. So what do we do here? Do you remember how to do such a thing? How do you integrate when you have a sine and exponential multiplied together? You have to do integration by parts twice, which gives you something like this. Now what do you do? No? Okay. You treat this equality like an equation to solve for this unknown integral. So this is my unknown, right? This is unknown. It's like x minus something minus 1 over s squared x. How do you solve for x? Move it here and then, yeah, right? Okay. So here's what you do. First, multiply s squared to get rid of all the s squared. Okay? That's going to go away. And then you move this to the other side and factor this out. And the result is that you have s squared plus 1 integral sine t e to the negative st dt. Right? There's no more of this. You have negative s sine t minus, oh, I shouldn't do that. Minus s sine t plus cosine t e to the negative st, right? And now all there is left to do is to divide by this, and you have the answer. And because, so these two are equal, but notice that we started with a definite integral. This is just the indefinite integral. So you put 0 to infinity. And that goes into t, right? S is a constant, so you don't mess with S. These values go into t. Now, we are going to assume that S is some positive constant number, so if you plug in infinity, that's going to be e to the negative infinity. What is e to the negative infinity? What's that?
0.
0, yeah, always the answer is 0, right? Okay, so this becomes 0 when you plug this in. Now, what would you get if you plug in 0? Sine of 0 is 0. Cosine 0 is 1. E to 0 is 1, right? So when infinity is plugged in as 0, minus negative s times 0 plus 1 over s squared plus 1 e to the 0th power, that's what you have. And of course, this is 1 over s squared plus 1. Okay? All right, so we got that, which verifies our result. Okay. Now, what do we see from this Laplace transform? Well, you see, if you feed in a function of t, it gives you back the function of s. Okay, so you feed in a function, you get another function. The difference is that originally it was a function of t, but now it's a function of s. Okay, in that case, we call that a transform. On the other hand, an operator is when you start with the function of one variable and it's the same variable, like derivative operator. Differentiation operator is x squared. If you differentiate, you get another function, which is 2x, has the same variable, right? So integral operator, differential operator, multiplication operator, all these things that we use in the differential equation world, they don't change the variable itself, whereas these ones, they change the variable, so that those are called transforms, okay? There's a third kind, which is called the, I forgot the third one, okay. All right, but I just wanted to point that out, okay? All right. So that's the Laplace transform. And the Fourier transform looks very similar, and the Fourier transform of f, usually this time we're going to often assume that the function is a function of x, and the definition is you integrate from negative infinity to positive infinity f of x of e to the negative ist. Oh, positive ist. So instead of a minus, you have an I. That's called a Fourier transform. Fourier transform. Forgot an R there. And you can see that again, this is going to give you a function of s. Okay. The problem is this one, when t goes to infinity, this rapidly decays to 0. How does an exponential function look like? This is what an exponential function looks like, right? It's like it starts at some value and then that's what an exponential function looks like. So if you integrate from 0 to infinity of this thing, it just quickly decays, so it converges for most functions, unless the function is increasing super exponentially, faster than the exponential function. This will always have a value. Okay? Whereas this one, you have to be careful. Okay? This one, if you just put a usual function like x, you're not going to be able to do the transform because that's not going to converge. Right? However, there are many classes of functions that do work, and one kind of functions that people like to work with, this one is called Schwarz class. Schwarz class. The problem is I don't know the spelling. I think there's like a bunch of mathematicians named Schwarz, and Some are spelled like TS and Z, and I'm not so sure which one it is. So I'm going to just scribble it. So okay. Sparse class is like functions where it goes to 0. So it's smooth, which means it's infinitely differentiable. Infinitely differentiable. So you can differentiate as much as you want. And limit of this function times e of kx x to infinity goes to 0 for certain positive k. So k is some positive k. So it's going down to 0 very fast. Fast like an exponential function of some power. Okay? And that's also true for negative infinity as well. So for negative infinity, you have to put, sorry, it should be, yeah. X going to negative infinity is also 0. Okay? For k negative. So those are called Schwarz class functions. And this is not really important, but for those functions, you can kind of see why this integral would be defined, right? Yeah. One important thing that we're going to be working a lot with is this thing e to the negative x squared. Because that definitely is in Schwarz class. You can differentiate this many times, and it looks like this. It has its maximum at 0, right? And it goes down quickly to 0. So this is what's called a Gauss curve, Gaussian curve, right? Your normal distribution is shaped like this, although you have to divide by some other ones to change. I think it's like 1 over square root of 2 pi or pi, something like this. That's called the normal distribution. But these functions, e to the negative x squared, that would be an important one to try. Okay. So my goal is to try to calculate this one. Okay? All right. And then the inverse transform. Oh, by the way, often we're going to write this as f of s. Okay? That's how we're going to write it. So this hat would be Fourier transform as a function of s. Okay? So inverse transform would be Fourier inversion of f hat s is defined as 1 over 2 pi of integral of negative infinity to infinity of f hat s of e to the negative ist ds. Oh, why did I put t here? Sorry, this should be x. Sorry, we changed the x. Okay, so that's the inverse transform. And what happens is that if you do this, you end up recovering your f of t. Now this is actually quite a contrast compared to the Laplace transform case. No differential equations book that's taught at undergraduate level would include the formula for Laplace inverse transform, because Laplace inverse transform requires some integration over the complex plane, and it's very complicated. I personally never have computed the Laplace inverse transform. What you do is you try to undo the Laplace transform by working backwards with the Laplace table. That's what people do. On the other hand, for inverse Fourier transforms, it looks almost identical as the other one, right? So people use it, and I actually want to show this at some point, not today, but probably on Monday I'll be able to do it. Not a rigorous proof, but some kind of like a proof, and in there I'm going to be using this fact actually. I'm going to use the fact that this is equal to 1 over s squared plus 1. That's why I did this interval. All right. So, where do I go from here? I want to talk about Gaussian integrals. And first of these being integral of e to the negative x squared dx 0 to infinity. Or actually, yeah, 0 to infinity. What's the antiderivative of e to the negative x squared? How would you do this?
U sub.
If you do u sub, what happens? U equals to negative x squared, du equals to negative 2x dx. So dx must equal to negative 1 over 2x du. So that becomes integral of e to the u, and then times negative 1 over 2x du. Now we don't like this because there's still an x, so you solve this for x by saying x is equal to square root of ui or something. So rewrite this as square root of u and then I. So this would be like I here. Doesn't look that.
No, that doesn't look.
Yeah, it doesn't look promising. So there are a few questions on calculus 2.
How about substituting negative x squared with ix?
It's not going to work.
X squared?
No, nothing's going to work. Okay. So this is an example of a integral question where you don't have an answer. Did you know that some integrals don't have an answer? Like sine x over x, this doesn't have an answer. E to the x over x, this doesn't have an answer either. Like many simple questions, you would think that there must be a way to do it. There is no answer. So, for example, if you put this on Wolfram Alpha, by the way, if you didn't know that website, it's like a website where you can cheat by like putting homework problems in and it does the integrals for you. Okay, so if you put this on Wolfram Alpha and it would just tell you it's an error function of some kind. And these give you some really strange answer, meaning that the antiderivatives are not the usual functions that you know, the logarithm, sine, or exponential functions. None of that is able to express the antiderivatives of these. So what people did was, like, for example, they needed this function, this antiderivative, so they would just define it as a new function. That's what they do. This is another important function. So they just define the antiderivative of this function as a new function. Okay. So what does that mean? That means this question is itself pretty ridiculous because you can't find the antiderivative. How are you going to find this definite integral? It requires some more trickery. And it also happens to be an integral that a lot of the physicists like to do. And if you want to major in statistics, because this is a Gaussian normal distribution, they also want to do this as well. So this is a pretty sought after problem that many physicists and statisticians want to learn. Okay. So let me show you how that's done. So first, what you do is you rewrite this twice. But the second time you write it as y. Now this is going to be, this and this will be the same value, right? It doesn't matter if you choose y or x, the value will be the same. And that means this squared will be this one. So let's do that. We're just going to find the square of this value first, and then later on take the square root. Okay, and that's going to be equal to 0 to infinity. 0 to infinity. Oh, just a minute. Oh, it has, sorry, so it has to be from negative infinity to positive. So if you integrate from negative infinity to positive infinity, you end up having e to the negative x squared times e to the negative y squared and dx dy. So I wrote it as a double integral. What I did was I moved this inside. Okay. That will be what's called the Fubini's theorem. Yeah, and Fubini's theorem is true if the thing is integrable. That quickly decays, so it's integrable. But then what does this mean? This means like you have on R2, you have this function where it has the maximum value at the center and it quickly decays over this entire domain you're trying to integrate. Okay. Now, because minus x squared minus y squared, that's like r, negative r squared, right? So what we want to do is we want to change to polar coordinates. So let's go to polar coordinates. So this will be negative r squared. R squared is x squared plus y squared, so that's what you have. Now, what did you learn about polar coordinates? Dx, dy, this is dA. In polar coordinates, what's dA equal to? I briefly mentioned a moment ago. Remember? R d theta anywhere? Yes. Remember that? Okay. So that's what we need. R d theta. Okay. Now, in order to cover the entire plane, R should go from where to where? So here's the entire plane. So we're trying to think of this as like this, right? So the radius should go to infinity from 0, right? How about theta?
Negative pi to pi.
0 to 2 pi. Or negative pi to pi. Okay. It's easier with 0 to 2 pi, so we'll use this one. Now, this is something we can calculate. This one's something we can calculate. How? Negative r squared is equal to u.
Yes.
Du would be negative 2r dr. Right? And do you see r dr? Right? So this would be negative. This would mean that negative 1/2 du is equal to r dr. So I can rewrite this. Now we have to be a little careful. When r is 0, u is 0. But when r is infinity, what happens to u? It goes to, let's not put the minus. I think that's less confusing. Okay? All right. In that case, when u is 0, when r is 0, u is 0. When r is infinity, u is infinity as well. So this didn't change at all. So we e to the negative u, and times 1/2 du, and then you still have d theta. Okay. Now, what's the integral of e to the negative u? Negative e to the negative u, right? You plug in infinity and 0. D theta, 0 to 2 pi. What do you get? Infinity What's e to the negative infinity? 0, right? And therefore you get 0 when you plug in infinity. When you plug in 0, you get negative 1/2. Well, you're subtracting it, so it's positive 1/2. Integrate by theta, it's 1/2 theta. Plug in 2 pi and 0, you get pi. So what do you get? What's the answer to the original question? So negative infinity to infinity of e to the negative x squared dx is equal to square root of pi. Very important. Okay. And by the way, sorry I started with this one, but nonetheless, this can be answered too. What would this be? It's symmetric, right? This is an even function, right? So this would be half of square root of pi, which is not that important. Now from here, we have another goal. The next goal for us is to put the next question. What if you have this, right? Now, one way might be like, oh, maybe we should try the same thing again, but then this would be like x squared times y squared, so it's not something pleasant, right? So there is this nice thing called Feynman trick. And the thing is that he's a physicist, and when he was in college, I don't know the actual professor who was teaching this. So his professor was teaching calculus at a very high level, and he learned it from his professor. But because he was using those results in physics a lot, this became to be known as the Feynman trick. So here's how you do it. First, step 1. Calculate e to the negative ax squared dx from negative infinity to infinity. Let's try this one. Now, if you take u as square root of a times x, then this will be simply negative u squared. Do you agree? So this is going to be negative infinity to infinity of e to the negative u squared. But then if you differentiate, du is equal to square root of a dx, so that dx equal to 1 over square root of a du. So instead of dx, you put 1 over square root of a du. Now, the boundary still doesn't change. If x is infinity, u would be infinity, if a is positive. It has to be positive. And if x is negative infinity, then u would also be negative infinity. So this is still true. Pull this out. What does this give you? What is this one?
Just pi.
Square root of pi.
Square root of pi.
So this is square root of pi over a. Now, step 2. And this is the amazing part. Differentiate both sides by a. Okay. It's very clever. So if you have negative infinity to infinity of e to the negative ax squared dx equal to square root of pi, and let's write it as a to the negative 1/2 power. We differentiate both sides by dA. How's that? Okay, first, what do you get if you differentiate this by a? What is e to the k times a if you differentiate by a? K e to the k, right? It's the same thing. It's just that negative x squared is that k, right? Okay? So what do you get if you differentiate this by a? Negative x squared e to the negative ax squared dx. Is that right? A. This is a times negative x squared, so that's the constant that comes out. Okay? How about on this side? Negative 1/2 comes down, square root of pi, you get a to the negative 3/2, right? Okay. How do you answer the original question then?
Well, the original is an even function. Oh, that doesn't.
Then set a as what?
Oh, 7.
A as what?
1.
1. Then what do you get? Negative x squared e to the negative x squared dx is equal to negative 1/2 of square root of pi. So you multiply by negative 1 and that's it. Oh, sorry. Okay. That's called the Feynman trick. You put a constant in, you do the integral, you differentiate both sides by that new constant, and suddenly you get result for other ones. Now if you differentiate this one more time, you can get the answer for x to the 4th power and 6th power and so on and so on. Right? Now notice that if x is odd, it's going to give you 0. X to the odd power of times this, it's going to give you 0 because it's an odd function over a symmetric domain. Okay? So on the homework for today, you're going to see some other Feynman tricks. So one is the homework is to find x to the 4th, right? And another one is I give you another integral that's depending on a value of a or something, and I'm asking you to differentiate that one as well to find the value of another pretty hard integral. And that's going to be part of the exam as well, because I don't know what to put for this part. All the other ones are very theoretical, so I don't want that to be there. So that's going to be part of the exam as well. Okay. All right, that's all for today.